So the next talk, according to my schedule, will be given by Jessika Valenciano. The person in the front of the room does not appear to be Jessika. So we are stuck with Dr. Clive Neal instead.
I'm the evil twin.
So Clive will be talking about the Highlands material Apollo 17 sample 73263,6. Clive, all yours.
Yeah, not to steal Jessica's thunder, but she did remind me that I made her give all the talks at LPSC, so we switched out for this one. I want to start by thanking the curatorial staff for magnificent job in getting these cores extracted, learning how to do it. Again, fortunately, Andrea is still there and passed on the knowledge. And let's make sure that we can keep that knowledge where it needs to be. There are other cores to be opened, and hopefully they will be opened in the not too distant future so that this initiative can actually continue, because new samples from the moon, fantastic. I mean, I've really enjoyed this workshop, and thank you, Chip, and the other organizers for bringing this consortium together, or these consortia together, because there are a variety. What we want to do, we started off this project by looking at Station 3 and getting some samples to look at that have already been thin sectioned from hand samples and also from rake samples. So looking at 73263, you can see what we're talking about, where it came from. We got the trench soils, we got the drive tubes, and we've also got the Apollo 17 traverse up in the top right. We've all seen the wonderful LRO pictures looking at that landslide deposit, or several landslide deposits. So we have geologic context. We had a geologist there to get these samples and put them in context. And if you have a chance to talk with Jack, he can still remember, I'd say, pretty much everything that went on in Apollo 17. So this is something that we have. It's a treasure to have that context in order to interpret the materials that were brought back. And now with the wonderful orbital data to go on top of that, we're in a unique position to actually move the science forward. So you can see where it's come from. We've got this landslide deposit on top of the Mare filled Taurus Littrow Valley. And this is the sample, or the thin section that we got, 73263,6. And what we focused in on was this somewhat coherent yet bashed up clast at the top here. When you look at it in polarized light, it looks it's beaten up. If you've been around for a few billion years, you'd be beaten up too. And it wouldn't look as good as you did when you were formed. And in a brief discussion with Chip and thinking about it last night, and busting Steve Simon's chops quite a bit, thinking about the nomenclature, if you've had a coarse-grained plutonic rock that has been beaten up by impact, you may find some of those lithologies in the finer grained materials, but you're looking for materials that could be unzoned if that's the case, and they would be fragments rather than welded together. What we have here is what looks to be a welded together clast included in this breccia material. And if we zoom in a bit more, we looked at this with electron microprobe. We got element maps. We then use laser ablation ICP-MS to look at the trace element mineral chemistry of the materials there. We've got basically pyroxene and plagioclase. The one thing that I see missing here is a scale bar, but hopefully it was over here. There it is. So there we can put it in context with the size of the grain. So this is not a plutonic rock based upon grain size. But you can see that it has been beaten up quite a bit, and maybe we've got this mechanical breakage that is causing that lower grain size. And when we look at the materials, we do the element maps here. We've got the magnesium, calcium, and iron. You can see the pyroxenes are exolved. So we have a slow cooling regime, and we've got two types of exsolution with this. We've got the lamella that you can see in the light blue, and then the Bleby exsolution also being shown in there. And the host pyroxene is the calcium-rich pyroxene. And then you can see the bright green being the plagioclase, which dominates this particular class. We've only got a portion of it there with regard to this particular element map. But it was the pyroxenes that intrigued us, because all of them seem to have undergone exsolution. So with that, what does that mean for these particular rocks? So we went in with the laser, and you can see we did our own impact study with the craters that were formed from the laser ablation analyses. And we were able to get data from the orthopyroxene exsolution, as well as the high calcium host pyroxene that remained. And then we got some analyses from the plagioclase around that. We're using about a 55 micron spot, and we were able to get some good data, but the fact that this had been beaten up was shown in the ablation, the way that the material ablated. It was not a pleasant ablation. Let's put it that way. So we ended up with spiky spectra rather than a nice smooth spectra as you go about it. So in looking at the data, they're not as clean as I would like, but they do show some interesting things. And we'll start off with the mineral chemistry here. And you can see we've got our two exsolved pyroxenes. And this is something to remember, that they form tight clusters down in the orthopyroxene enstatite or iron-rich enstatite, and up in the augite fields in this. And we see a similar sort of thing going on in 60025. But we also see there some of the original pyroxene that would plot. And is there a laser pointer on here? Top button. Oh yes, there we go. That would plot around about here, but we don't see this in this small class. Remember, 60025 is pretty big compared to this little nugget that we got in the thin section. So these have undergone slow cooling. They've undergone subsolidus equilibration. I say we already talked about the different types of exsolution. So the next thing to do is to explore the kinetics behind this and try and do some more detailed work within there. But that is still TBD and to be done, not to be determined. So we've got slow cooling from a plutonic or intrusive magma body to give us this subsolidus reequilibration. If we look at the where it plots in the magnesium number anorthite percent in these samples, you can see that it is relatively evolved, not only in terms of the magnesium number, but also the anorthite. And that was a surprise. And it actually, it is unique, I imagine, but when you see the range that we have, there are rare examples of that in the sample collection. But what is unique is the range in anorthite versus the MG number. Now that's only about 4 anorthite units, but that's quite broad for an anorthosite. And it plots outside the normal sort of field for Apollo samples. So the augites are also MG rich relative to the orthopyroxenes. And you think, well, it's an iron rich enstatite, but they do contain more magnesium. So there's been some things that have been going on. And if we look at the rare earth elements from the plagioclase, you see typical rare earth elements. And I do point out the spikiness here that we got because of that unpleasant ablation. But there's this very distinct positive europium anomaly, light rare earth enriched. But when we look at the low calcium and high calcium pyroxenes, this is what we see. We've got the red being the orthopyroxenes and the green being the high calcium pyroxenes. And what you notice is there is no negative europium anomaly, which you would expect if it was co-crystallizing with the plagioclase. So puzzling. They could not have come from the same liquid. But what we think has happened here, if we compare that with the 60025, you've got high calciums, averages from 73263 for high and low calcium pyroxene, and then also from the different 60025 thin sections, and similar sort of thing down in for plagioclase. And what we think has happened during that slow cooling and that re-equilibration to give you the X solution, you have had equilibration of the pyroxene with plagioclase, which has allowed or destroyed the negative europium anomaly. So when we go and look at try and calculate some equilibrium liquids, we basically have to keep that in mind, that the pyroxenes have been disturbed, but have the plagioclases. So we're going to follow a similar method, and if you want me to use up the time, I can explain the method, but that may be a bit dry. Needless to say, we use the major element compositions of the pyroxene or the orthopyroxene to calculate partition coefficients. And similar sort of thing with the plagioclase. And what you've got plotted on there in the lines, it represents a field of magma ocean evolution based upon various models that you can see in the legend to the right. So we've got the plagioclase up there with the orange circles, and they're representing something that is highly evolved. You can see if you go from left to right, up in the top right there, you can see high K creep or creep, where that plots. That's the ultimate evolution of those different magma ocean crystallization trends.
2-minute warning.
Really? All right, great. I'm almost done. Almost. What you see also there for three of the models are the 95, 97.4, and 96.4% crystallized solid. So to the right of that, we're in the last 3 to 5%, and that's where the plagioclases plot. The orthopyroxenes, you can see there, are not plotting in the magma ocean field because they have been disturbed due to subsolidus re-equilibration. But the plagioclase looks good. So if we go back to the plots here, you can see that both the pyroxenes and the plagioclase have elevated rare earth element profiles compared to 60025. So it's 60025 must have crystallized earlier in the magma ocean sequence if we're following that. And if we plot the 60025 plagioclases, you can see where they plot relative to the 236. Bloody hell, too many numbers. And you can see they plot a little earlier, but not that much earlier, unless we had an extended crystallization sequence. So this is something that plagioclase appears to be unaffected, but pyroxene seems to be affected. Now, did the process that affect those pyroxenes disturb the isochrons? Lars is not here unless he's in the ether. But this is something to consider that we pointed out in the Tosivia and Neal paper earlier this year. So, summary and conclusions, we see that it's relatively unique because it is evolved, and especially in terms of the plagioclase compositions. If we just take the trace elements at face value, you can say that pyroxene and plagioclase did not crystallize from the same magma because there is no negative europium anomaly. But if we take the petrography and see the X solution, we've had subsolidus reequilibration of the plagioclases. And the plagioclase appears to be robust in trying to calculate relative timing of the Faroe and anorthosites in terms of calculating their equilibrium liquids and putting them in the context of the crystallization of the lunar magma ocean. And again, I want to thank Jessika for doing all the work. And again, thank the organizers for this meeting, and again, curatorial staff, fantastic job. Thanks very much.